Welcome to Study Loop.
So continuing on with some physical chemistry work here, we're going to be taking a look at a few more different calculations. And so we have a cross-section of a drum with radius r, length L, and it carries fluid flowing along with a height of h inside the drum. So we have the following. This is h. We have L, that is the length. And then we have 2r, that is the radius. So we know the density and the mass flow through the cylinder, so we can solve for the volume flow rate using differential equations. So the time taken to reach the point is 11.5 hours. So you do get that in minutes, but you can just convert it into hours. So if you have it in minutes, your time will be 690 minutes. Multiply it by 1 hour divided by 60 minutes, you get 11.5 hours. And so for the height of the liquid inside the drum, we can use a different expression now, where we have V is m over density. We sub in some of our values. Substitute in our radius, 1 meter length, we've solved to be 5 meters at this point. And so the height of the liquid in the drum is 0.539 meters. Then we can solve for the input mass flow rate. That is 85.6 kilograms per minute. So as the flow tended to fluctuate considerably throughout, the surge drum is inserted to maintain a constant downstream flow rate, even when the upstream flow rate arises. So still, the rate of the liquid drainage inside the drum will vary as the height of the fluid inside the drum increases. So a signal directly proportional to the control valve will be set up to provide better performance to the drum by maintaining optimum flow of the liquid that would be drained inside the drum. So this will reduce fluctuation and it will provide more stable flow for the processing unit.